Hi everyone, so this is the lecture video on timing analysis. So timing analysis is a method to validate whether the timing performance of the circuit we design fulfill the timing requirements or not by checking all the possible timing paths. So all the possible timing paths may include the path starting from input to the input of the flip-flop, the path starting from the input and ending at the output, or the path starting from the flip-flop and ending at the output, or the path starting from a flip-flop and ending at a flip-flop. So a complete static timing analysis consists of mainly these three steps. First, we identify all the timing paths of the circuit as mentioned in the previous slides. And then second, each path's delay will be calculated. And the last step is to check the violation of the timing constraints for each path. As you know, so the checking of the timing constraints involve mainly the setup time checking and the hold time checking. Before we go further to the details, first please get familiarized with the terms including clock period and the clock to Q delay. So clock period means the duration of time for the clock signal to complete a pulse that start from 0 to 1 or 1 to 0. So the clock period is as shown in one other example here, where it is from this point to this point is the duration of time for this clock signal to complete a pulse which start from 0, go to 1, and then come down to 0 again. The second term you need to know is the clock to Q delay. So clock to Q delay is the time, the delay time required by a flip-flop to transfer the signal from D to Q. So we start to count the time from the clock edge. That's why it is called clock to Q. Okay, clock to Q, which means once a clock edge happens, we start to count how long it takes for the D signal, in this case 1, to transfer to Q, here 1. So the symbol we use in this lecture is T, C to Q, stand for delay of the clock to Q. Okay, besides, there are two more terms you need to know the definition, which is the setup time and the hold time. Setup time, or TS, is the minimum amount of time the data signal should be held steady before the clock event or the clock edge, so that the data are reliably sampled by the clock. So let's look at the signal below here. There are two waveforms. Let's focus on the clock signal for the flip-flop 2. Okay, and let's look at the setup capture edge here. So the setup time means if before the clock edge of the flip-flop 2 happen, the data should be ready at the input D of the flip-flop. Okay, how earlier it should be ready? It should be should reach at this point, the latest at this point of time. Okay, at this point of time, which is setup time earlier. Okay, counting from this clock edge of flip-flop 2. Okay. Whereas the hold time is the minimum amount of time the data signal should be held steady after the clock event, so that the data are reliably sampled. Okay, let's again look at the clock signal of flip-flop 2. Okay, so let's look at the edge, the first edge of the clock signal. So that means after the edge happened, at this point of time, the signal at the D, at the input D, still need to be there stably for the how long? For the duration of TH, the duration of hold time, so that the data transfer to the Q can happen with stably without issues such as metastability or wrong signal being captured. Okay, based on the definition of the clock period, the delay of the clock to Q, setup time and hold time. Now let's look at how we do the timing analysis, which include the setup time analysis and the hold time analysis. There is a scenario where there's a delay happen to the clock routing, which we call clock skew, but for the first example, we ignore the clock skew. Okay. So that means the timing parameters involved only include the clock period, the clock to Q delay, and setup time, hold time, and the logic delay coming from the gates in the circuit. Okay. So the logic delay coming from the circuits of the combinational logic is denoted using the symbol TPD, the propagation delay coming from the logic gates. Okay. So let's say we have a circuit look like this, where it consists of two flip-flops, flip-flop 1 and flip-flop 2, and between flip-flop 1 and flip-flop 2 there is a combinational logic connecting the Q of the flip-flop 1 to the D of the flip-flop 2. Okay, so when you do the setup time analysis, The complete timing analysis, as mentioned earlier, will involve all the paths, but here in this lecture, we will show or demonstrate for the critical or worst case scenario, where we will consider the longest path delay for the setup time analysis and shortest path for the hold time analysis. Okay, now let's look at the setup time analysis. So the flip-flops that launch the signal is called the launch flip-flops. So the edge of the flip-flop 1 is called a launch edge, whereas the flip-flop that capture the signal is called the capture flip-flop, and the clock signal, which is a clock FF2, okay, that capture the signal is called capture edge. So since we are doing the setup time analysis, so we call the edge as setup launch edge, referring to this clock, and setup capture edge, referring to the clock of flip-flop 2. Okay. So when the signal move from the D input of flip-flop 1 launch in the launching process from FF1, it will go through the flip-flop. Okay, so that's why the delay involved will be TC to Q, and the signal launch from the flip-flop 1 will go through the logic gates. That's why it will experience the TPD delay, the delay coming from the logic elements inside, and reach the destination flip-flop, which is flip-flop 2. As mentioned, the signal cannot reach too late. It must reach in advance. How earlier it should reach? It should reach not later than a point of time where it is setup time before the capture edge. Okay, now let's look at the example of setup time analysis using a very simple circuit which consists of just a flip-flop, D flip-flop, and an inverter. And this flip-flop has the setup time 0.6 nanosecond, hold time 0.4 nanosecond, and clock to Q delay minimum 0.8, maximum 1.0. And the inverter delay, the TPD involved here, involves only the one inverter, and its delay is 1.1 nanosecond. So now let's draw the circuit such that we can see the how the signal start from a launching flip-flop, which is the only flip-flop, and ending up at the same flip-flop. Okay, so that means this flip-flop will act as a launching flip-flop as well as the capturing flip-flop. Okay, so we draw it so that you can see how it is launched and captured later. So when it is launched, the delay involved is the TC to Q of this flop, and the signal after launch will move from D to Q, and it will move through the logic element, which is the inverter here. So the delay involved is TPD. Okay. So in the timing waveform, you can draw two clock signal. One is the launching clock and the other is the capturing clock. Okay? Since in this simple circuit, the launching clock and the capturing clock the same, okay, so we label it the same, and we still draw two so that you can see that the launch happened here, okay, that involves the delay of the T clock to Q and the delay of the inverter, and the capture edge is here. So as mentioned, the delay coming from the TC to Q and TPD should not exceed this point of time, because the signal should reach in advance, as mentioned earlier. Okay, so when we calculate the delay, so we consider the TC to Q 1 nanosecond, which is the maximum range because we want to consider the worst case scenario in 1 nanosecond plus the inverter delay 1.1 nanosecond. Okay, and so 1 nanosecond, 1.1 nanosecond, and we should make sure that after considering the TS, the setup time, okay, after we sum up these three elements, the TC to Q, TPD, and the setup time, the sum should be not more than the clock period. Okay, the clock period. Okay, so because from this point to this point is the clock period. Okay, so the sum of 1 plus 1.1 and plus 0.6 should not exceed the clock period. Okay, so 2.7 nanosecond. Okay, so if this path we are analyzed is the worst case scenario, which means if this is the path with the longest delay, then we will be able to know the best clock period we can apply on this circuit. So 2.7 nanosecond, let's say, is the longest delay we can find in this circuit. Then we can use 2.7 nanosecond as the best clock period we can apply, the shortest clock period possibly to be applied. Then we can use it to compute the best clock frequency we can apply for the circuit, which is the reciprocal of 2.7 nanosecond, which is 370 megahertz. While for hold time analysis, hold time analysis normally involve the shortest delay because we want to check whether the signal at D, okay, at D input of a flip-flop stay for the duration of hold time after the clock age, okay, without being overwritten by a new value. Okay. So that means the signal that coming from the launch flip-flop cannot reach too fast and override the input D of the capture flip-flop. Okay. So now let's look at the timing waveform below. So the first clock signal is the clock signal of the launching flip-flop, and the second clock signal is the clock signal of the capturing flip-flop, which is FF2 here. Okay. So after the flip-flop 1 launched a new signal from D to Q. Okay, let me see. Okay. So at the same time, the flip-flop 2 also transfer the data from D to Q. Okay, at the same time, or when the age happened here. Okay, but the hold time analysis will check whether from the age, the new signal coming from the flip-flop 1 undergoing the logic elements delay will override the input D of the capturing flip-flop too fast or not. If it happens too fast, that means the TC to Q plus the TPD is shorter than T hold time, Okay, so this is not a good case because this means the new signal, okay, coming from the launch flip-flop reach the D input of the capturing flip-flop too fast. Okay, the O value stay not long enough. Okay, so it will not guarantee the transfer of the data from at the flip-flop 2 happen correctly or not. So the delay from from flip-flop 1 TC to Q undergoing the TPD should be longer than the hold time, so that it doesn't override the input D of the flip-flop 2 too fast. Let's look at the example using the same circuit. So say the flip-flop D, okay, this flip-flop launch the signal 1, okay, from D to Q. Okay, so this involves the TC to Q. Okay, and next going through the inverter. Okay, going through the inverter and override the O value of the D input here. Okay, and that delay is TPD. So it shouldn't happen too early as shown in this arrow. It should happen later, which is exceeding the hold time counting from the age of the capture flip-flop, okay, such that it doesn't affect the transfer of the signal from D to Q of the capturing flip-flop. But in this case, note that capturing flip-flop is the same as launching flip-flop. Okay, so let's check. In this case, it happened, the violation happened or not. So we take the worst case scenario. So we take the minimum TC to Q for the hold time analysis plus the inverter delay, okay, which is 0.8 nanosecond plus 1.1 nanosecond, which is 1.9 nanosecond. So the 1.9 nanosecond is the delay of TC to Q and the inverter delay. So we check whether it's greater than the hold time or not. If it is greater than the hold time, then it is safe. So the hold time given here is 0.4 nanosecond. That means it's greater than hold time. So in this circuit, there is no hold time violation happened. Now let's look at the second example for setup time analysis, again without the clock skew. Okay, so first we identify the critical path delay, okay, which is normally involve the longest path, like shown in this slide. And then we check the delay that happened, which involve the TC to Q for the flip-flop 0, okay, TC to Q for the flip-flop 0, and the propagation delay that involve the 3 AND gates, A0, A1, A2, and 1 XOR gates. Okay. Okay, so with all the delay considered here, which is TC to Q and TPD, we need to make sure that the delay, the signal reach at the input D of the launching clock F3 in advance, which is not later than T, setup time counting from the age of the capture clock. Okay, so if this is a critical path, then the sum up of the delay should be not greater than the clock period. Clock period is from here to here. Okay? Or from here to here, same thing in this case. Okay. So in this case, the delay involved is 6.4 nanosecond. So the best clock is 156 megahertz. For hold time analysis, we normally will first get the shortest path and then we check the delay involved here. Is it too short, and override the O value of the D2 earlier? So we use the rules here, which is TC to Q minimum plus TPD. So it should be longer than the hold time, counting from the capture H. Okay, so it is 0.8 nanosecond, the TC to Q, plus the gate delay 1.2 nanosecond. The total is 2 nanosecond. So we check the hold time is 0.4 nanosecond. So that means 2 nanosecond is greater than 0.4 nanosecond. So no hold time variation happened. In the real case, normally there is a delay coming from the clock routing, because the same clock source need to be routed to multiple of the clock ports of the flip-flops. Okay, so there are some delay occur. The farther away the flip-flop is located, the longer delay will happen to the clock port of that flip-flop. So this kind of delay is called clock skew. So as you see here, say the original clock shown in clock 1 without any clock skew. When there is some delay on the wire before it reach the clock port of flip-flop 2, and this caused the clock pulses that happen to flip-flop 2 shifted a bit from the original clock signal. The further shifting will happen to clock 3 because there are more delays, and also similarly happen to clock 4. Okay, let's consider the same circuit, but this one with the clock skew for the clock port at flip-flop number 3. So let's see whether the previous timing analysis, setup timing analysis, is still workable here to find the best clock period. Again, let's identify the longest path delay, which is as highlighted here. And let's look at the timing waveform where of the first clock signal, which is labeled as clock F0, which is the launching clock F0, and the third clock signal, clock F3, is the capturing clock signal for capturing clock F3. And notice that there is a shifted signal of clock F3 compared to clock F0 due to the clock skew of 1.5 nanosecond. So the blue arrow again highlight the delay that involved from launching clock to the capturing clock. So the delay involved will be the clock to Q delay, TC to Q, the TPD, the propagation delay involving a gate A0, A1, A2, and X3. And the signal after the delay must reach input D of capturing clock in advance, which is setup time earlier than the capture clock H. So please note that the whole window of time considered for the delay and the setup time is longer than the window of the clock period, because the window involves a clock period plus the clock skew. So the clock period plus the clock skew should be greater or equal to those timing parameter involved, which are the delay and the setup time. So when you want to consider the clock period using this path, so the formula becomes clock period greater or equal than TC to Q, TPD plus TS minus the clock skew, as shown here. So the clock period using this path should be at least 4.9 nanosecond. And note that the delay plus the setup time has been deducted from using the clock skew 1.5 nanosecond. So a question arises. So the 4.9 nanosecond is the worst case scenario or not, since some deduction has happened here due to the skew. So to double check this, you can do the analysis by using the second longest path delay. So the second longest path delay is actually illustrated here, that involves A0, A1, and X2. So look at the waveform that involves clocks, launching clock and the capturing clock. And the delay involved here is highlighted by this blue arrow. So from the launching clock to the capture clock, the delay that involved is TC to Q plus the TPD, which involves A0, A1, and X2, and the signal should arrive at the latest at this point of time, where this point is setup time earlier than the capture H. So now let's look at analyze the best clock that we can apply using this path. So it is 5.2 nanoseconds. So please note that this 5.2 nanosecond is longer than the 4.9 nanosecond taken or computed using the longest delay path. Okay, this is because in this case there is no skew, so the window of time involved here is exactly the window of time for the clock period, and you will see that 5.2 nanosecond is longer clock period needed. So if you have many possible clock period computed from the same circuit, then we normally take the longest one. Like in this case, we take 5.2 nanosecond, the best clock, because the 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 clock that coming from the worst case will be able to be applied for all the timing paths of the same circuit. Okay, so using this to compute the best frequency, we will get 192 megahertz as the frequency to be applied on this circuit. So for whole time analysis that involve clock skew, okay, so what happened? Okay, you can. I hope this illustration will show you the whole time analysis involving the clock skew is different from the one without clock skew. So say the positive clock skew have happened to the capturing clock FF2, then you see there's a shifted clock signal FF2 here compared to the FF1. So the delay involved in the whole time analysis, which is TC2Q and the TPD. Okay. Now the delay that the minimum delay you need here will be longer compared to the case without clock skew, because as you can see here, now the delay involved here need to be larger. Not only the whole time, it need to be larger than the whole time plus the skew, okay, which is become more difficult to achieve compared to the case without clock skew. Because if we imagine you take out the clock skew, the delay of the shortest path will be easily greater than whole time. But if you plus something else, in this case plus the skew, then you need the delay requirement need to be fulfilled, become tougher compared to the case without skew. Okay, so with this consideration, let's do the analysis on the same circuit. So the shortest path you need to choose is the worst case scenario. That means you choose the shortest path that involve the skew at the clock skew at the capturing flux. So in this case, you can choose this shortest path. Because if you choose the shortest path that involves X2 only, it doesn't involving the clock skew. So the situation is not as tough as the path that involves the clock skew. Okay. Okay, so we need to check whether this requirement is fulfilled or not in order to check violation is there or not. So the TC2Q 0.8 nanosecond plus the 2 gate delay 1.2 times 2, so we get 3.2 nanosecond. So 3.2 nanosecond, we need to check whether it's greater than whole time plus skew or not. So in this case, whole time plus skew is 1.9 nanosecond. Luckily, it's still greater. That means no whole time violation happened. Okay, so that's all for this video for the timing analysis that involve setup time to get the best clock frequency and whole time analysis to check whether got whole time violation or not. Thank you.